Nucleophilic substitution reaction. So this is a very common types of chemical reaction that we see in organic chemistry. And overall, this is the types of chemical reaction that we can use to transfer, to change or transform one functional group into another functional group. And how that is possible is that one of the functional group is replacing or substituting another functional group, therefore becoming another functional group. And if we were to look at this diagram right here, this shows the overall view of what happened in a nucleophilic substitution reaction. So here in this case, we have our starting material, and we call this the substrate. It then reacted with this reagent Y, whatever Y would be. And in the course of a chemical reaction, Y is coming in to replace X, or substituted X. Thus, therefore, we see this is a substitution reaction. And in the course of the chemical reaction, X then breaks off and taking the electron with it. And we will then refer to X as the leaving group. So overall, that is the big view of nucleophilic substitution reaction. And by recognizing this, we will be able to identify whether it is a product of a nucleophilic substitution reaction or not. And again, if we see one functional group is replacing another group, then we know it is a nucleophilic substitution reaction. Now, we use some terminology to describe this reaction right here. So let's go over some of the terminology so make sure we are familiar with them. First, the starting material in this case is then referred to as the substrate. And the substrate in this case right here is also the electrophile. It is the electrophile because in the course of this reaction, it is accepting electron. And Y here is then referred to as the nucleophile. And sometimes we say nuc, short for nucleophile. And the function of the nucleophile is then donating electron. So that's actually what happened in the course of this reaction. The reagent Y is serving as a nucleophile, giving electron to the substrates. And as the nucleophile then give the electron to the substrate, it actually will be given electron to a very, very particular atom in it. And it will be this carbon right here. This carbon right here is the electrophilic carbon. And in order for it to be an electrophilic carbon, the functional group X in here has to be a group that is taking electron from this carbon, thus making this carbon electrophilic. So this, therefore, the lone pair of electron from the nucleophile come in to attack this carbon. And now kicking off this X right here. And thus X is taken off with the electron with it. So therefore, we call this the leaving group. A leaving group is abbreviated as LG. And here is our product. And we will be looking at the mechanism of this reaction in great detail in a little bit. But the leaving group has to be a group that is capable of separating from the substrate and taking the electron from the substrate with it. So it has to be a particular type of functional group that will be able to handle the electron because it will be taking the electron with it. And overall, we will then see that electron in the course of this reaction are ultimately being transferred from the nucleophile into the leaving group. So the electron initially start out on the nucleophile and end up on this leaving group. So the nucleophile first gives the electron to the carbon, exceeding octet for this carbon. So the carbon will then give the electron to this X, and X is then taken off with its electron. So again, electrons are being transferred between the nucleophile into the leaving group. And one can imagine this reaction right here may be reversible. If the product form is not stable, then this reaction may be reversible. So how do we know? if whether this reaction will be possible or not. So now let's go over this. Again, we see that electrons are ultimately being transferred between the nucleophile and the leaving group. If the electrons are more stable on the leaving group, so let's say the leaving group have more stable electron than the nucleophile, then this reaction will then be thermodynamically favored. Reaction is thermodynamically favored. And if we were to have the opposite, if the electrons on the leaving group, whatever this leaving group may be, is not as stable as the electron on the nucleophile. So let's say here have more stable electron, then this reaction right here may happen. However, it is not thermodynamically favored. So not thermodynamically favored. And again, we will explore everything about this in a little bit. How to determine the stability of the leaving group and the nucleophile and the reaction mechanism. There are two possible mechanisms for a nucleophilic substitution reaction, and we call the first one the concerted process and the second one the stepwise process. So these are the two mechanisms in which how a nucleophilic substitution reaction may happen. And both of them can happen depending on what is the substrate and what is the nucleophile and so on. But there are two possible mechanisms, and depending on the mechanism that is taking place, different products may be formed. So what is the concerted process? The concerted process is basically the mechanism in which we have the nucleophilic attack and the loss of the leaving group occur simultaneously, meaning they happen at the same time. As the nucleophile coming to attack the electrophilic carbon, it then breaks off the leaving group, and the leaving group breaks off at the same time. So all happen. So the mechanism of this reaction is as follows. Let's say here we have the nucleophile with a lone pair of electron. And now let's say make this negative to make this a very good nucleophile. And here is the substrate with the leaving group. So in this case right here, in this mechanism, both the nucleophilic attack. So the nucleophilic attack is the step where the nucleophile is donating an electron into this electrophilic carbon. And again, the leaving group has to be a particular functional group that is pulling electron away from this carbon, making this carbon right here electrophilic. And once this carbon right here is attacked by the nucleophile, it exceeds its electron, its octet. So therefore, it has to give this electron right here into the leaving group. And the leaving group therefore breaks up with the electron. So therefore, in this case right here, the product that we will then form is as follows. The nucleophile is now bonded to this carbon, and the leaving group breaks up, taking its electron with it. Notice this lone pair electron right here. This used to be the electron that were part of this bond over here, and now end up on the leaving group. And now the leaving group would then become negative in this case. So this is called the concerted process, where the two steps happen simultaneously. And later on, we will refer to this mechanism as an SN2 mechanism. The other mechanism that is also possible is something we call the stepwise process. So what happened in the stepwise process is that the two steps do not happen at the same time, but one after the other, in which the step that happened first is the loss of the leaving group. So the leaving group breaks off first to form an intermediate And the nucleophile then come in to attack the intermediate. So these two steps right here happen at different time, one after the other. And the mechanism of this reaction is then as follows. So let's see here we have our substrate with the leaving group. So the first step that will happen is then the loss of the leaving group will happen first. So the loss of leaving group. In this case, the mechanism just show the step referring to the loss of leaving group is as follows. The leaving group steals the electron from the carbon, breaks up, and taking the electron with it. And now, if we were to follow this arrow, this carbon right here will become a carbocation, and the leaving group breaks up with its electron. So this step is again called the loss of leaving group. And now we have ourselves an intermediate. In order for this step to happen, the intermediate has to be one that can stabilize itself. If this intermediate right here is not stable, then we will not see this stepwise process mechanism right here. And again, we will discuss this in more detail in a little bit. So this happened first, followed by the nucleophilic attack. So here we have our nucleophile. The nucleophile will then come in, donate an electron into this electrophilic carbon, and that is called the nucleophilic attack. And the bond between the nucleophile and the carbon is now formed. And that will be our products. And we will then refer to this mechanism later as an SN1 mechanism. Now, these are the two steps that may be possible right here, the two types of mechanism that are possible. Which one will be formed then? Then the answer, it depends on several factors. So in this case right here, factor that favor whether the reaction would undergo SN1 and SN2. We'll list some of those factors in a little bit. But depending on whichever mechanism that the reaction would happen, it will affect different types. It will have a different types of reaction rate, and also side product and major product, and also stereoselectivity as well. So again, depending on which reaction mechanism take place, the reaction rate may be different. And second, the major and the minor product that are produced may be different as well. And third, these two types of mechanism have different stereoselectivity. One is stereoselective and the other is not. And we'll discuss this in further detail in a little bit. So, depending on whether the reaction is a follow an SN1 or an SN2 mechanism, these are the differences that they can produce. So how do we know whether it would undergo SN1 or SN2? The answer, it depends on this following factor. First, what is the nucleophile? The types of nucleophile can affect whether the reaction would undergo an SN1 or SN2 mechanism. Second, the substrate. What kind of substrate do we have? While one substrate may favor SN1, the other may favor SN2, and another may favor both SN1 and SN2 without much selectivity at all. And the third factor, the leaving group. What kind of leaving group do we have? This can also affect the reaction mechanism. And fourth, the reaction condition. By changing the reaction condition, we can also control or favor either an SN1 or an SN2 reaction mechanism. Now, so this is a summary of the different types of steps that can happen in a nucleophilic substitution reaction. And we have discussed this in the previous lecture already. So it's very important that you are able to name each of this and recognize what is happening in each of these steps. So first, a nucleophilic attack, again, as a reminder to all of you, is the step where we have a nucleophile coming to attack an electrophilic carbon. So this is called the nucleophilic attack. So in this case, the electron, so this is our nucleophile, and this is our carbon. And the next step is the loss of the leaving group. So the loss of the leaving group is basically when we have something in functional group that is capable of breaking up and taking the electron away from the carbon. So here in this case right here, the mechanism of this step, it basically involves an electron from this bond, the bond between this carbon and this bromine, taken up, and the electron go to the bromine. Now, the electron can only go to the bromine, but not the carbon, right? And the reason is the electron will always go to the more electronegative atom. If we were to draw the opposite of this mechanism, for example, this step, this will be wrong. It does not make sense because this says that the carbon is gaining an electron from the bromine, and we know this does not happen. And if we were to follow this step, then this carbon then would then become a carbocation over here. And now this is the intermediate. Both of this are now intermediate. Now this step right here may be reversible because once we form these two intermediate, the bromine can come back in and attack this again, and this will then be called the nucleophilic attack. So the nucleophilic attack and the loss of the leaving group are the two opposite steps of each other. But it does not produce anything else productive. And as for the proton transfer step, again, this is the acid and base reaction. And this may be a step that you will see in nucleophilic substitution reaction. And again, the proton transfer step is basically where we have an atom with a lone pair of electron that is basic, and that come in, pick up a proton from the acid, breaks up this electron here, and now this electron go to the acid. And as the product, we would then be having this product over here. And one thing very important that we need to remember is whether or not a proton transfer will happen, whether acid and base reaction. Again, proton transfer is acid and base reaction. In order to figure out whether this reaction right here, this step may happen, we have to be looking at pKa. pKa is a quantitative tool that we have to determine whether this step will happen or not. So here in this case, we need to be comparing this pKa. So let's say this is pKa1, and over here, pKa2. And if pKa2 were to be greater than pKa1, then we know this reaction will happen. Versus if it's the opposite, then it will not be as likely. It can still happen, but not would be the one that will happen in high yield. And lastly, the rearrangement. Again, so this refers to the carbocation rearrangement. We have seen how carbocation can rearrange before. So if we were to have a secondary or a primary carbocation, these are not very stable. So if we were to have a methyl group or a hydrogen on the nearby atom, in this case right here, either a methyl group or a hydrogen, the methyl or the hydrogen group can migrate over by taking breaks off this electron right here, come in and attack this carbon right here. And again, this is called the carbocation rearrangement. If we still remember, it can be called 1,2 methyl shift or 1,2 hydride shift. a hydride shift can happen before a metal shift if there is a hydrogen to migrate. So make sure you are familiar with all of this step, understand how each of this arrow means, and be able to draw the corresponding product. And again, it is very important that we follow the electrons. Each of this arrow has a very special meaning to it, and we need to be able to understand what each of the arrow means and how to draw the corresponding product correctly. And this basically serves as the basis to be able to figure out any reaction mechanism that you will see later. So now let's try some exercise. Below are some of the product of the nucleophilic substitution reaction. And we are giving you the product and we're asking you to figure out. So in this case right here, we've been told that this first reaction right here is a concerted mechanism. Knowing this is a concerted mechanism, please figure out, draw the reaction mechanism for this. And the second one is a stepwise mechanism. Please draw the mechanism of this reaction. So let's go over A first, the concerted mechanism. So here we've been told that this product right here are formed through a concerted mechanism. And if we were to be looking at the overall reaction, we will then see the hydroxy group is coming in to replace the bromine functional group. So here in this case, we know that the hydroxy group is the nucleophile, and the bromine is then the leaving group. So this is our leaving group, and this hydroxy group right here is the nucleophile. Now we can go ahead and ignore the sodium because this is an ionic compound. When we dissolve this in solution, then the sodium and the hydroxy group simply break apart, and that is our nucleophile right there. So here in this case right here, we will then see, because we've been told this is the concerted mechanism, meaning that the nucleophilic attack and a loss of the leaving group happens simultaneously. So here in this case, let's draw this molecule again and draw its mechanism. So I will go ahead and ignore the sodium because the sodium is actually have broken off already. So here in this case, that's what we would have. And now we would then, again, I would recommend drawing out this lone pair of electron, so that way we can start drawing our arrow from this lone pair of electron. So this come in to attack this carbon. Now again, make sure you understand why it come in to attack this carbon right here, because we will then see this carbon right here is very electrophilic. Why it is electrophilic? Because the bromine is taking the electron from it. So the bond between the carbon and this bromine, this is a very polar covalent bond. So the carbon is lacking electron, thus attract in the electron from the nucleophile, and the nucleophile come in to attack this carbon. Once this carbon had received the electron from the nucleophile, it is now exceeding octet. So we would then see it have to break the electron and give the electron to this bromine. And there you go. Following this arrow, we will be able to draw this product. Oops. And the bromine is now breaking up with the electron with it, and now it be becoming negative. So one of the lone pair of electron in here was the electron that the bromine had with the carbon earlier, and now the carbon is given that pair of electrons, the electron to the bromine. So that's what we will have in here. Now just to make sure why that we can see that the electron is ultimately being donated from this oxygen. This is the starting point where the electron was originally in, and now ultimately it's now being transferred to the bromine, and now this is the ending point with the electron end up in. And if we were to be able to figure out why did this make sense, then it actually makes sense because initially on this starting material on the reactant side, electron is starting out on a hydroxy group. And now electron end up on a bromine group to form this bromide. And we will then see that this is more stable. Electron on a bromide is more stable than the electron on the hydroxy group. And therefore, electron will be transferred, or reaction will happen to make sure we can put the electron on the more stable species. So that's what this reaction would make sense. Now, we would never draw this reaction mechanism this way. And I will go over this to make sure that we know this is something to avoid because it does not make sense. If we were to draw this coming to attack this bromine, and now I'm going to draw the lone pair electron in here. Is it possible that this hydroxy group come in to attack this bromine? And the answer would then be no. And the reason why, if we were coming to attack this bromine, the electron would now have to break up and donate to the carbon. And so in this case right here, we see electron being transferred from a bromine to a carbon. And that does not make sense because the bromine is a more electronegative atom that want to take the electron from the carbon, not the other way around. And if we were to follow this arrow, let's assume this happened, and we will follow this arrow, then we'll be having this product right here. That would be the product that we found. And we can see how unstable this would be. Why? Because this carbon ion right here is really, really unstable. And this is also very, very unstable as well. So therefore, chemical reaction will not happen to produce unstable substances because this is not favorable. And hopefully that helps us understand why that the steps in a concerted mechanism is as far as what we have seen. First, this come in to attack this electrophilic carbon. And the electron between this carbon and the bromine is now breaking up. And this bond right here that used to form this electron is now going to the bromine. And that's how we could transfer electron to the bromine. By first transfer the electron to the carbon, and the carbon then give an electron to the bromine. That's how we would transfer electron from the nucleophile into the leaving group, not donate an electron directly into the leaving group. And now let's try example B. So why don't you take a minute before we go over this together. Assume you have a minute already. Let's now draw the mechanism of this reaction. So here in this case, we see the following. When we compare the reactant and the product side, we would then see that the bromine has been replaced by this OH group. Where did this OH group come from? Well, it actually comes from water. So the OH group from water is acting as a nucleophile and come in, donate electron to the carbon. They connecting to this bromine and replacing that bromine. So that's why this is also a nucleophilic substitution reaction. So the OH from water is replacing the bromine. And now let's draw the mechanism of this reaction. So here in this case right here, we are being told that this undergo a stepwise mechanism. A stepwise mechanism means that one step happens first before the other. And again, the step that happened first is first the loss of the leaving group, followed by the nucleophilic attack. So let's draw the substrate again so we can draw this reaction mechanism. So the first thing will happen will then be the bromine. The leaving group in this case breaks up and takes the electron away from it. And again, only this error would happen in this way, but not the other way around as follows, because that does not make any sense. That means that the bromine is given electron to a carbon, and we know that bromine will not do that, since it is a more electronegative atom than the carbon. Again, please understand this. And if we were to follow this arrow right here, then we would have the following. So we will form these two intermediate. And in this case right here, we have a tertiary carbocation. Now we know that tertiary carbocations are stable than compared to secondary or primary. So this is one of the reasons why it can happen. It can happen because we are producing an intermediate that is somewhat stable, but still not stable enough for it to exist by itself. And once we have produced these two intermediate already to form the product, that when we have water, once we form this carbocation in here, it becomes very, very electrophilic. So it will attract electron. Now it can attract the electron from the bromide, where the bromide come in to attack this again. And therefore this step right here will then be reversible. If the bromide come in to attack, then we'll go back to the started material, and that will not produce anything productive. The other step that can also happen is where we would have the electron from the nucleophile come in to donate to the electrophilic carbon over here. So in this case, the other possibility, one that will be more productive because we producing something new, and where this lone pair electron from the nucleophile come in and attack that. So again, this is the nucleophilic attack from water. And when we follow this arrow over here, we will be producing this product. And now be very careful. This oxygen right here will become positive because it starts out being neutral. When it donates a pair of electrons to form a bond to this carbon, the oxygen is given one electron away. So it will go from neutral to being positive. And as for this carbocation, when this arrow is being drawn to it, it means that it's gaining one electron. So therefore it goes from positive to now neutral. And that's what we would have. And once we have this already, then the next step is with this bromide right here acting as a base. We know this is not a very good base, but here in this case right here, to explain the formation of our product and how we form HBr, we have to draw this step. However, this step right here, it can happen. It is not unlikely, it can happen. And the reason why is because this pK over here, this is now an acidic proton. And because it is an acidic proton, its pK is about -2 to -3, so it is somewhat acidic. Therefore, allowing the bromide to come in, acting as a base, and doing the proton transfer. So this is the proton transfer step right here. Now again, this step right here is not very, very likely, but it can still happen. And we will be producing this product and HBr. So there you go. Let's now have you try some of this reaction right here. So why don't you take a minute to work on this before we go over the answer together. So in this case, we are no longer giving you the product, but we want you to be able to figure out what would be the product of this reaction. And it actually is not that difficult at all. So let's try this. So here in this case, on A, we would then see that so one thing good that would be good for us to start doing is to analyze the electron density on this molecule to figure out which carbon is nucleophilic or which atom is nucleophilic or electrophilic, so we can determine what will happen. So here in this case right here, we see here that it's very easy to see because one, we know this oxygen right here is negative. then this oxygen is very rich in electron. And anything that is rich in electron can be nucleophilic. So now we know this is our nucleophile. And here in this case right here, the bond between this carbon and this bromine right here, it is a polar covalent bond where electron is been shifted to the bromine. So therefore we now know that this carbon right here is electrophilic. So there you go. We have a nucleophile and the electrophile both happen in the same molecule. And because of rotation around this carbon-carbon single bond, this molecule can actually twist around, in which this nucleophile can be very close to this carbon. So therefore it come in and attack this carbon right here, breaking up the electron, giving the electron to the bromine. And as a consequence, we now be forming a ring. Now, how many member ring will we form? One good thing for us to do this is start labeling the atom. Let's say we call this to be atom 1, 2, 3, 4, 5. We will be forming a 5-member ring with the oxygen in it. So there you go. This oxygen will be oxygen 1, 2, 3, 4, 5. That's how we would keep track of it. So the bond happened between oxygen 1 and the carbon 5. And now the bromine breaks off with the electron, take an electron with it, so it becomes the bromine. So that's pretty easy, right? All we have to do is identify our nucleophile and our substrate with the leaving group. What is the leaving groups? Once we identify that, we'll be able to take the nucleophile and substitute the position of the leaving group. So now let's try B. Here in B, so this we do have a substrate in here, and so we can know that this carbon in here, this is the electrophilic carbon. So what is this molecule right here? Now, please see that this is an ionic compound, right? Because the bond between sodium and sulfur, this is an ionic bond. So this molecule is actually as follows, where there is a negative charge on the sulfur. And because now we see the negative charge on the sulfur, this means this sulfur right here is rich in electron. So that is our nucleophile. So here in this case right here, the nucleophile will come in to replace this bromine. And the product that we would then have would then be this product. And the bromine is the leaving group. And there you go. So here in this problem, we just want you to be able to figure out what the product would be. And we will go over the reaction mechanism in a little bit. Here in this case right here, if you were to thinking whether this reaction would undergo an SN1 or SN2 mechanism, then the answer is that this actually is an SN1 mechanism. Whereas the example in problem A, this is an SN2 mechanism. But again, we'll go over how do we determine whether it will undergo an SN1 or an SN2 mechanism later. And we still have the sodium, so we should put the sodium in here so that they can counter and neutralize the charges. And on this problem C right here, when we analyze this, we can see this is our material. And again, this carbon right here, because it is bonded to an iodine, this is the electrophilic carbon in here. So that carbon is serving as an electrophile. And here in this case, we have this molecule. There is an ionic bond in here. So that basically means there is a negative charge on the oxygen. And thus the oxygen is our nucleophile. And this is our leaving group. So this is our leaving group. And this is our nucleophile. So the nucleophile come in to replace the leaving group and to draw the product. And again, we keep the substrate mostly the same. And now we simply change the leaving group into the nucleophile. And now the iodine, the leaving group breaks up and taking the electron with it and becoming negative. So this will be the product of this reaction. And again, we're going to put the sodium in, so that way that will counter the negative charge on the iodine to form an ionic compound.